Foundational models in computer vision are becoming more and more prevalent these days. With advent of the ability to create large foundational models, all different fields, be it computer vision, be it robotics, natural language, they are leveraging the power of foundational models, which are trained on large corpuses of data on big compute clusters that can be used in downstream tasks or can be fine-tuned towards particular applications. Segment Anything by Meta, Segment Anything 2 by Meta is an example of a foundational model for the task of semantic segmentation. Now we are seeing a lot of models being released for monocular depth estimation. These foundational models for monocular depth estimations have been trained using millions of images of data, and they are showcasing some amazing results. In this video, we're going to talk about another foundational depth model, DepthAnything. For those of you who are not familiar with monocular depth estimation, monocular depth estimation essentially means estimating the depth of a scene from a single image. Just using a single viewpoint, you are trying to estimate depth of different objects or to obtain the geometry of that scene. A dense depth map from a single image. That is what the problem of monocular depth estimation is. If you want to learn more, here is our another video. We talk in detail about monocular depth estimation and typically talk about another foundational model by Apple, which is Apple's ML Depth Pro. In this video, we're going to talk about DepthAnything. This is a model from TikTok and other university labs, including Hong Kong University. We'll talk about DepthAnything, what it is, what it does. We'll talk about how it's trained, what the architecture is, and then we will see how it's set up and what the results look like. So stay tuned until the end of this video. Welcome back to the channel, guys. My name is Roop. I'm a computer vision engineer at Convolve. At Convolve, we assist small, medium, large enterprises with computer vision, robotics, AI-based solutions. If you are facing some issues, you are trying to solve problems, and you think a computer vision application, robotic application, AI-based application can assist you, and I'm sure it can in some parts of your business. Here is our contact information. Feel free to reach out to us. We'll be happy to discuss your issues, discuss the potential outcomes, the potential to improve your workflows, to improve your business, and have a chat regarding that. So here is the contact information again. Please reach out to us. So guys, coming back to DepthAnything model. So guys, here on the screen, you can see the project page for DepthAnything. This was a paper in CVPR 2024. Unleashing the power of large-scale urban unlabeled dataset. So guys, this model essentially portrays that not only they are using a labeled corpus, but they are using 60 times, almost 60 or 65 times unlabeled dataset as compared to the labeled set. So they have around 1.5 million images for labeled set, and they have around 62 million plus unlabeled images. And in this particular paper, in this method, they've showcased the ability to leverage the unlabeled dataset from the internet to be able to train this foundational model with amazing results. So guys, here you can see some of the images and their predicted depth map by this method. They have trained this model on 1.5 million labeled images and around 62 million plus unlabeled images jointly. So for this particular method, they use the teacher-student model, the knowledge distillation framework, to be able to leverage unlabeled dataset as well. So here essentially their foundation model has the following features. It's able to do zero-shot relative depth estimation, zero-shot metric depth estimation, and an optimal in-domain fine-tuning and evaluation, right? So essentially you can do relative depth estimation, metric depth estimation, and on top of that, using a foundational model like this, you can fine-tune on your dataset, on the target domain dataset, and you can see and obtain amazing results from there. Here the authors have shown the comparison between Midas, which was another baseline that they're comparing against, and depth anything, and you can see that the depth is a lot crisper, a lot sharper. Especially you see the net of the basketball basket, and you can see that this is a lot smoother, a lot crisper as compared to Midas, which has some blurriness here, right? The depth is not crisp. So that's essentially what the model is capable of. On top of that, they have also showcased that they are able to use this output depth along with control net, uh, which is a generative model, to produce new images, to be able to produce and generate new images given a geometry. So for example, you give it a scene geometry as a depth map, and it's able to generate visuals, it's able to generate images on top of that geometry, which is pretty nice. Guys, then again, some more results on videos. We can see that here the input video is very blurry, and the previous best method gives a blurry depth estimate, whereas the depth anything method gives a very crisp depth estimate. And the reason behind this, we'll see. They apply a certain augmentation to uh, the training of the model, which really helps in achieving this better result on blurred or poor quality input videos or input images. All right, guys, so let's go into and look at the paper here. So here is the paper. They have posted it on archive, and you can go through this paper. So let's just quickly go to the framework. So guys, the overall framework for this particular method is over here. Um, the idea is that there is a model, student model, and then there is a teacher model. The teacher model is trained using labeled dataset. So this teacher model has been trained using labeled depth ground truth dataset, and it is so called the teacher in this setting. It's the expert. Um, and then there is a student model which does not know much, which does not know anything. And the idea is that you take a labeled image, you take an unlabeled image, you pass it through the model, and then the model is going to predict a depth map for the labeled image, and is also going to predict a depth map for the unlabeled image, right? For the labeled image, you already have the ground truth. You have the ground truth data. Maybe it came from LiDAR, it came from stereo matching, or it came from structure from motion. You just have all the depth map ground truth data for that particular labeled image, and you use that for supervision. For the unlabeled image, what you do is you use your teacher model to predict a depth map that essentially acts as a pseudo label for that particular image. Using that pseudo label, you supervise the unlabeled part, and all the losses are back propagated to further train this student model. If you want to know more details, you can go through the paper, and it has all the details about the math and the losses and everything else that the authors are using. One thing, guys, the authors talk about, and I want to point that out, is um, essentially the author said that unfortunately in our pilot studies, uh, they were not able to gain much advantage using a self-training pipeline that they have showcased. Um, and that was because with already sufficient labeled images, the extra knowledge acquired from unlabeled was a little limited. So because they had 1.5 million labeled images already, whatever they were getting from the extra was not really helping improve the accuracy. And what they did was they essentially uh, challenged the student model. So we proposed to challenge the student model with the more difficult optimization target for additional visual knowledge on unlabeled images. Now, essentially, to make the task, the training task, a little challenging for the student model, they essentially inject strong perturbations to unlabeled images during training. So these are the perturbations. They are injecting these perturbations on top of the unlabeled images, they are using some augmentation techniques. What these augmentation techniques are helping with is that it is compelling the student model to actively seek extra visual knowledge and acquire invariant representations from unlabeled images. So after you add those augmentations, and these augmentations basically are two form. One is perturbation, which is color distortion, including color jittering and Gaussian blurring, and the other is strong spatial distortion using the cut mix method. So using these augmentation, Gaussian blurring, color distortions, and spatial distortion, uh, this is essentially forcing the model to essentially reason the underlying geometry of the scene and not just blindly predict the depth from a clear crisp image, but when given distorted, when given a blurry image, it's then able to reason the geometry of the scene. It's able to better understand what's going on and predict a better depth map. So that's how, and this basically helps this model obtain a very good depth estimate. On top of that, they are applying some semantic preservation. This essentially is another enforcing method to enforce that the model looks at the correct features, right? So this is a pre-trained encoder from the Dino model, and they are essentially doing a cosine similarity. So here is the semantic assisted perception part of this paper. What the authors are doing, they are essentially comparing the features that are output from the encoder that the authors are training and the pre-trained encoder. They're comparing the two in order to enforce the encoder that they're training to learn features that are relevant, that are semantically accurate, that are semantically relevant. So that's how this model is going to work, and it's trained. And all these are the reasons why this kind of a blurry input still leads to a very nice depth estimate, as you can see on the screen. Now guys, let's talk about the code. So the authors have made the code public. All of it is open source and it's available on GitHub. So this is the repository for DepthAnything project, and here they have given very clear instructions on how to install and run this model. It's pretty straightforward. You just clone the repository and you install the required Python dependencies, and then running it is pretty simple. These are some example commands. If you want to run it on some images, this is the command, and if you want to run it on a video, then this is the command. So there's two scripts that the authors have given. Here is the entire code, and these are the run commands which are going to run inference using a pre-trained model. So guys, now all of these weights, the encoder and the model weights, basically when you run this, will be downloaded from the internet, and they could be used for your inference purpose. They have provided all the pre-trained weights. You don't need to worry about any of that. Now what we did was we took all of this, and essentially we ran it on our own examples. Now here is the code for the DepthAnything model, and we ran inference on first of all the example videos. So this is the command to run inference. We ran it, and you can see it downloaded the weights for the model, the encoder model, and it was able to then do the inference. So let's quickly take a look at the results. So this is the output, taking a little bit to load here, and here you can see the output depth maps, which is very similar to what we'd seen on the output website, which showed the results for this method. Now guys, what we did was we wanted to test how this method performs on an autonomous driving dataset, and for that we ran it on the virtual KT2 dataset. So virtual KT2 dataset, for those of you who don't know, looks something like this, and these are the images, and there's a car moving, ego car is moving on the street, and then we wanted to see how the depth estimates are on this kind of dataset. So we ran this model and we got some results. So let me show you the output result here. So here you can see the output on virtual kitty. So I just pause it. You can see that it's able to predict the depth. Now these are normalized depth maps that are being visualized here. Here is the raw image. And it's able to, give a good depth estimate. Depth estimates are pretty nice and smooth. Um, and here we can see going through the entire sequence, right? Um, So this was our result on the virtual kitty. Now guys, keep in mind that you can always use such a foundation model and you can fine tune it on your own dataset. Now with the monocular depths, there is a scaling issue always. The output of a monocular depth estimation model may not be uh, absolute, may not be accurate to scale. Relatively, it may be correct, but in an absolute sense, it may not be. So that's where some fine tuning comes into the picture in order to ensure that if you are running it on a scene, the output from that particular model is actually to the correct scale and you're getting accurate results. Now, we didn't do much evaluation with regards to the accuracy of the depth maps that were produced for the virtual kitty and do some error metrics on that yet. But overall, just did a qualitative evaluation looking at the depth maps or seeing how it looks with regards to the geometry, with regards to the crispness of the depth maps, and looks pretty reasonable. So that's it for this video, guys. We've talked about the DepthAnything model. We've talked about what the major contributions are and how it works at a very high level. We've talked about how we can set up this repository and run it. And then we've seen results on their sample videos and also seen the results on the virtual KT2 dataset. If you like this video, please hit the like button, subscribe to the channel, and hit that bell icon so you are notified about any new videos that we upload. We keep uploading videos about computer vision, robotics, AI. So this is the channel you want to subscribe to. Again, thanks for tuning in, guys, and I'll see you in the next video.